everyone, Chapter 3 Periodic Table. In 3.2 Periodicity, you will learn about the atomic radius in variations across period, first row transition element, and down a group. And you also need to compare with the ion, which is you will see the variations of the ions for the period 2 and 3. You will see the isoelectronic ion, which is you have to define and compare the radius between the isoelectronic ion. Periodicity is the periodic trend in the properties of the elements. Atomic radii, it relates to the radius, which is radius is the half of the distance between the nuclei of the two adjacent identical atoms. For the example here, there are two atoms, okay, and this is a nuclei or nucleus, and the distance between these two nucleus is the radius. Let's see the variations in atomic radii. So in variations in atomic radii, you will learn the variations across period and down a group. Across period, the main factors affecting the atomic radii is effective nuclear charge, or the symbol is ZEFF. It also known as a ZEF. And down a group, shielding or screening effect is the main factors that affecting the atomic radii. So these two factors affecting the variations in atomic radii across period and down a group. So this is the diagram showing the variations in the atomic radii across period and down a group. You can see that the atomic radius decreases across period and the atomic radius increases down a group. Effective nuclear charge. What is the effective nuclear charge? It is the net positive charge experienced by the valence electrons. There are calculations for the effective nuclear charge, but you don't need to calculate the effective nuclear charge, but I just showing you how to get the effective nuclear charge by calculations. So for the example, okay, this is a formula. ZEF equal to the Z proton number minus to the number of the electrons filled at the inner shell. So this is a sigma symbol, okay, it refers to the number of the electrons filled at the inner shell. When the effective nuclear charge ZEF increases, the nucleus attraction between or towards the electrons becomes stronger, and the nucleus, it will pull the outer electrons closer, and the atomic radius becomes smaller. Example, there are chlorine with the proton number is 17, magnesium 12, and this is the electronic configuration for the chlorine, and this is the atom, okay, atom model for the chlorine, and then okay, this is how to calculate the ZEF for the chlorine, which is the 17 we refer to the proton number minus to the 10. Okay, 10 is the inner electron. So before this, okay, in 3.1 you have learned that the highest end is the energy level where the outer electron or valence electron occupy the orbital. So this is the outer electron or valence electron, and this one, the previous electron in the inner shell, okay, inner shell we refer to the n equal to 1 and 2, okay, electron that occupy in this orbital is inner electron in the inner shell. So there are 6 plus 2 plus 2, 10 inner electron, and Zeph, it is positive 7. So the atomic radius of the chlorine is smaller because the nucleus pull the outer electrons closer with the charge of positive 7. It shows that each of the electron, it will felt the positive charge with the positive 7. The value is the positive 7. Okay, let's see for the magnesium. This is an electronic configuration for the magnesium. So the outer electron, you can see that there are 2 outer electron or valence electron occupied in the orbital 3s. So this is the atomic model for the magnesium. And Zeph, okay, because it has a 12 proton number minus to the 10 inner electron, so it is positive 2. So it shows that each of the electrons, okay, it only felt positive 2, the effective nuclear charge. Okay, so that's why it shows that the attractions, the attractions are weaker. Okay, and then it will cause the atomic size become bigger. So you can see that the atomic size of the magnesium bigger compared to the chlorine, because each of the electron in chlorine, it will felt positive 7 of the effective nuclear charge. But for the electron in magnesium, each of the electron in it only felt positive 2 of the effective nuclear charge. So that's why the attractions, okay, between the nucleus and electrons in the magnesium weaker. It will cause the atomic size of the magnesium bigger. And because of the effective nuclear charge, okay, for each electron in chlorine are stronger, okay, between the nucleus and electron. So it will cause the size, the atomic size become smaller. And if we compare between the chlorine and magnesium, of course the magnesium has bigger size compared to the chlorine. Okay, let's see exercise 1. So this exercise in need you to rank each set of the main group elements in order of decreasing atomic size. Main group elements, we refer to the elements is located in the block S and P. So it needs you to briefly explain your answer. So let's see the answer. So this is the electronic configuration for the potassium. Okay, I just showed you the outer electron or valence electron. Okay, this one is the short form for the electronic configurations of the argon. Okay, elements are of the same period. So you can see that all the elements are in the same period because highest n is 4. So it shows that all the elements at the same period. And across the period from the potassium to the gallium, okay, you can see that the proton number are increased. Okay, 19, 20, 31. Okay, so the proton number are increased. So if the proton number increase, it will cause the effective nuclear charge increase. Okay, because these 3 elements, okay, are located at the same period. So you have to see the factors of the effective nuclear charge. And effective nuclear charge, it relates to the number of protons. Hence, the atomic size is reduced. Okay, let's see another example. Okay, this is the electronic configurations, okay, for the bromine, krypton and rubidium. So you see that bromine and krypton, okay, are element in the same period, but the bromine has less proton number compared to the krypton. Okay, krypton there are 36, but bromine 35. Okay, only one krypton. It shows that krypton has more proton, okay, compared to the bromine. So it shows that the bromine has lower effective nuclear charge compared to the krypton, and it shows that bromine larger size compared to the krypton. And rubidium, okay, it has a higher energy level, period 5. So if compared with the bromine and krypton, it is located at the period 5 for the rubidium. So of course the inner shell is increased, okay, and the shell for the elements at the different shell, okay, factors that can affect the atomic radii is the shielding effect. So the shielding effect for the rubidium, okay, larger or increase or stronger, and that's why the atomic size for the rubidium is bigger. Okay, let's see the shielding effects. It also known as screening effect, and is caused by the mutual repulsion between the electrons of the inner shell and the electrons occupy the valence shell. It also occurs between the electrons, okay, in the same shell, okay, but it's less effective compared to that electrons in the different shell. So this is an example. It gives you the lithium, sodium, and potassium. So you can see that the difference between these three atoms are shell. Lithium, it only has 2 shell, okay. Sodium, it has 3 shell, okay, because it is located at the period 3. And potassium, it has more shell, okay, compared to the lithium and sodium. So for the second point, it said that screening effect is caused by the mutual repulsion between the electrons of the inner shell. So this is the inner shell, okay. The last shell is the outer shell for the outer electron, or we call it as a valence electron, okay. This is a valence electron. All right, so okay, between the electron, we know that the charge for the electron is negative. So negative and negative, there will be repulsions. So repulsions, it will cause the mutual repulsions, okay, between the inner electrons. But it also said that the electrons in the same shell, okay, if the electrons located in the same shell, okay, it less effective. The repulsion is less effective compared to the electrons at the different shells. So electron at the different shells, okay, it will cause like this one, okay, it will cause more repulsions compared to the electron at the same shell. Okay, so let's see, this is let's say this one is the outer electron, and nucleus, we have the positively charged nucleus, and this one is the inner electron. So as I told you, okay, the electrons, the charge for the electron is negative, so between the electron there will be repulsions, okay. There will be repulsion between the electrons in the same shell or between the electron in the different shell. So this show that repulsion occur between the electron at the same shell, and this one is the repulsions occur between the electron at the different shell. Okay, so another one, and there are also attractions, okay, because positively charged nucleus, this one is the positive charge, so we know that between the positive and negative, okay, it will be attractions. So at the same time, it have attractions. So inner electron shield outer electron more effectively. So outer electron, it will feel less attraction from the nucleus. Okay, when it has the inner electron, okay, the inner electron, it will cause the repulsions, and it will cause the attraction between the nucleus and outer electron weaker. So that's why the atomic size become bigger. Okay, let's see. This is elements, okay, for the period, for the group 1. Okay, we have the lithium here, okay, should be Li, I at the right side, okay, not below. Okay, this one is the lithium. Okay, we have the sodium, potassium, rubidium, cesium, and francium. So all this one is at the same group. Okay, group 1. All right, but the difference, the similarity of the elements is all the elements has the same valence electron. So you see that, okay, all the element has one valence electron, but the difference is you can see that the atomic radii, okay, down a group the atomic radii increases. Why? Okay, because down a group the number of the inner shell increases. So when the number of the inner shells increases, you can see that from the electronic configurations, okay, the number of the inner shell increases, so it will cause the shielding effect increase. And when the shielding effect increase, shielding effect is caused by the inner electron, okay, and it will cause the attractions between the nucleus and the outer electron or valence electron become weaker. Okay, weaker attractive forces between the proton in the nucleus and valence electron. And valence electron are loosely held, and it will cause size of the atoms increases. Okay, next, let's see exercise 2. Okay, arrange the following sets of the atoms in order of the increase in size. Explain. So the answer is this one. It gives you this one, and the answer is, okay, this one. Okay, increasing atomic size. Beryllium has a smaller size compared to the magnesium and calcium. Okay, you can, if the question asks you to rank, okay, you may rank like this one. Okay, you put the comma, but must be complete with the arrow, and you state the increasing atomic size. If you don't want to draw the arrow and write the increasing atomic size, you can use symbol of the greater than, okay, which is calcium greater than magnesium greater than beryllium. Alright, so this is a electronic configurations, okay, because to rank this element you need to write the electronic configurations. From the electronic configurations you can determine, okay, which one has the smaller size and bigger size. So clearly from the electronic configuration you can see that beryllium, okay, highest end is 2, but magnesium 3 and calcium 4. So all these elements are in the same group, but what is the difference is the shell. So down, okay, so the elements, okay, with the less number of shell, okay, it will have smaller size compared to the element with the that have more number of shell, just like this one, calcium. So that's why, okay, the rank, the list, okay, like this one, okay, beryllium has smaller, followed by the magnesium, and the bigger one is the calcium. So these elements are in the same group, okay, group 2. Moving down a group, alright, moving down a group, you can see that the number of shell increases, okay. So this one has 2 shell, this one 3, and this one 4. Okay, this will increase the shielding effect, okay, hence the bigger atomic size. Okay, let's see. Okay, this is a summary, okay, for the variations in atomic radii. Okay, across period, I told you that the proton, the factors, the main factors that affect the atomic radii across period is the effective nuclear charge, which is effective nuclear charge is caused by the proton number. So proton number increases from this point, okay, you will know that the effective nuclear charge increases. So it will cause the attraction between the valence electron or outer electron and nucleus become stronger, and the atomic size smaller. Okay, this is a variations in atomic radii across period. Remember, okay, the main factors affecting the atomic radii across period is the effective nuclear charge. So this is all points, okay, you need to explain. And down a group, okay, down a group, the main factors that affecting the atomic radii is the shielding effect or straining effect. And what caused the straining effect or this shielding effect? Okay, it is number of shell. So number of shell where the inner shell, okay, it has inner electron. So this inner electron, it will shield the outer electron or valence electron, felt the attractions from the nucleus. So that's why the down a group, number of shell increase, shielding effect increases, or you want to use the terms screening effect, it also can. Okay, and it will cause the attractions between the valence electron and nucleus weaker because inner electron, as I told you, okay, it will shield the outer or valence electron from felt the attraction from the nucleus, and it will cause the atomic size increases. So this is a summary for the variations in atomic radii. Okay, next, let's see the variations for the elements across the first row of the transitions elements. So this is the elements for the first row of the transitions element at the period 4. Okay, starting from the scandium until zinc. So this one, okay, in the 3.1, okay, I show you that the valence electronic configurations, okay, for the scandium is the 4s2 3d1. So for the titanium, okay, still 4s2 because all these elements are in period 4, and the next electron it will occupy in orbital d, so it becomes 3d2. Okay, so for the vanadium 3d3, okay, until the zinc, okay, it will end up here 4s2 3d10. Okay, so the electron is added into the orbital d. Okay, so let's see the variations in atomic radii. Okay, this is a graph. Okay, it shows that you can see actually the variations of the atomic radii for the transitions element is not like across period and down a group. Okay, for the other elements. Okay, because you can see that it is quite similar. Okay, we cannot see clearly, okay, the variations of the atomic radii, okay, whether it is increase or decrease. Okay, so it quite constant. Okay, the atomic radius of the transitions element is almost constant across the period actually. So why it happened? Okay, this is because the atomic size do not change significantly across the period. And why it happened? Because the electron are added to the inner d orbitals. I show you, okay, that electron is added to the d orbital, and the d electrons, 3d electrons, it will shield the outer 4s electron from the attractive force of the nucleus. Thus, okay, the increase of the nuclear charge number of proton is cancelled by the increase of the shielding effect caused by the additional inner electron. So that's why you can see that the atomic radius for the transitions element, first row of the transitions element, quite same or quite constant. Okay, this is the reasons, okay, why the atomic radius quite constant for the elements, first row of the elements for the transitions element. Okay, next, comparison atomic radii and its ionic radii. Okay, let's see. For the example, we have group 1, Okay, this is a group 1. Sorry. Okay, this is a group 1 and this is a group 17. Alright, so this is ion. Okay, you see that this one lithium, lithium plus, sodium, sodium plus, potassium, potassium plus, okay, rubidium, rubidium plus, and cesium, cesium plus. Okay, this one is the anion of the group 17, okay, atom of the fluorine, chlorine, bromine, and iodine. So what is the difference? You can see that for the group 1, okay, you can see that the atom, okay, this is a radius, so atom, neutral atom has the larger size compared to the ions. Okay, means that if you can see that lithium it has larger size compared to the lithium plus. Okay, and for the group 17, the ion, okay, is larger compared to the neutral atom. For the example here, you see that the iodine, okay, is larger radius compared to the iodine of the neutral atom. So why it happened? Okay, let's see. Okay, for the first one, this we see the sodium for the group 1. Okay, this is a sodium neutral atom. It has the number of the protons 11 and number of the electrons also 11 for the neutral atom. But when it becomes ion, positive ion, okay, it will release 1 electrons, remove 1 electron. The number of protons still same, 11, but the number of electron become 10 because it removed 1 electron. So what happened? Okay, it only has 10 electron compared to its neutral atom, so it will cause the attractions between the nucleus and remaining electron. Okay, the 10 electron is the remaining electron after it remove 1 electron. It will become stronger, okay, because it has less electron now, so the attraction will become stronger. So when the attraction becomes stronger, that's why the size of the ions for the group 1, okay, it will smaller compared to its neutral atom. Okay, let's see this one. Okay, this one, it shows you the electronic configurations. So how the cation form when it loses one of the valence electrons. Okay, because sodium is group 1, so it will remove 1 electron from the neutral atom to form Na+. So this is the electronic configurations for the Na+. So you see that the neutral atom and cation have the same number of protons, but positive ions of the sodium, it contains less electrons or number of shell than its neutral atom. So what happened? It will cause the attractive forces between the nucleus and remaining electron is greater than in the neutral atom. So you have to use terms remaining electron for the ions, okay, because it remove 1 electron from the neutral atom, so the electron remain is 10, and thus, okay, the size of the cation is smaller than its neutral atom. Okay, let's see for the anion. Chlorine, for the neutral atom, it has 17 protons, and of course the number of electrons same as the number of protons, 17. And anion, negative ion, it shows that it will gain 1 more electron, so the number of electrons become 18. So the number of electron is increased than its neutral atom. So when the number of electron increase, what happened is, okay, you see that the anion larger than compared to its neutral atom. Okay, an ion is formed when an atom accepts electron. So proton number still same, but the chlorine has more chloride ions has more electrons than its neutral atom. So when more electron is added, we know that electron and electron, it will cause repulsions. So it will cause more repulsions occur in Cl- ion. So when more repulsions occur in Cl- ion. That's why the attractions become the nucleus and outer electron weaker. So that's why the size of an ion larger compared to its neutral atom. Okay, so you also can use this term. Okay, the repulsion causes the electron cloud spread out and the outer orbital expand. Okay, exercise 1. Choose the larger particle in each pair between aluminium and aluminium 3+. Of course, the larger one is aluminium. Why? Because when it compared with the positive ions, okay, aluminium has more electron compared to the positive ion. That's why it has larger size compared to the positive ion. And for the neutral atom and an ion, because an ion, it gains the neutral atom will gain electron to form the anion, so electron increase, and when the electron increase, it will cause the repulsions. So when the electron repulsion increase, attraction become weaker. That's why the size of the S2 minus always larger compared to its neutral atom. Okay, let's see the cation and anions. Cations, it is formed when the neutral atom loses electrons, okay, whether one or more than electrons, and anions form when a neutral atom gains electron. So less for the cations, when it loses electron, it will cause less electrons repulsions. So electrons are removed from the valence shell. And for the anions, when electron is added to the neutral atom, it will cause the greater electrons repulsions, and electrons are added to the valence shell. And what happened to the cations, okay, when less electron repulsions, so it will cause the attractions between the nucleus and remaining electrons closer to the nucleus. But for the anions, it will cause the electron cloud spread out. And okay, this one I said just now. Okay, and okay, what happened to the electron cloud for the cation? It will shrink, but for the electron cloud for the anions, it will expand. And the last one, that's why for the cations, okay, it is always smaller compared to the neutral atom, but for the anion, larger than neutral atom. Okay, let's see the isoelectronic. Isoelectronic, we refer to the isoelectronic species, we refer to the group of the atoms or ions having the same electronic configurations. Okay, this is the keywords for the isoelectronic species. It refers to the atoms or ions with the same electronic configurations. For the example, okay, when this ion, when it becomes ions, okay, you see that the electronic configurations are same. Okay, all the ions has the 1s2 to s2 2p6. So we call this species, okay, this ion as isoelectronic ions. Why? It is called isoelectronic ions because have same electronic configurations. So why? Okay, the electronic configurations are same, but you can see here, okay, the size are different. You see that the more positive charge, the smaller species. For the example, Na+, we have the Na+, Mg2+, aluminium 3+ ion. And you see that, okay, the more positive, okay, aluminium, it is 3+, so it is a smaller species. So you can see that's a size smaller compared to the magnesium 2+ and sodium+. And for the anions, okay, the more negative charge, the larger species. So you see that comparison between F-, O2- and N3-. So this is a N3-. The 3-, so it is more negative. That's why it has larger size compared to the O2 minus and F minus. So why it happened? Okay, because when proton number increase, the effective nuclear charge also increase, and the attraction between the nucleus and remaining electron stronger. Okay, all the species actually has the same proton number, but the have the same number of electron, but the proton number still same. And you can see that this is a Z value. The attractions become stronger when it removes the electron. So that's why the ionic radii decreases. Therefore, you can see that when we arrange, okay, this species, okay, N3 minus, actually, if we compare between the anion and cation, anion always larger than cation. So you see that anion, N3 minus, O2 minus, F minus, larger compared to the cation Na plus, Mg2 plus, and aluminium 3 plus. But between the anion, of course, the more negative, okay, it has a larger size compared to the O2 minus and F minus. And between the cation, of course, the more positive is smaller compared to the magnesium 2 plus and Na plus. Okay, so this is an isoelectronic species. Okay, exercise 2. Write the electronic configurations of these ions and indicate which are isoelectronic. So this one, okay, you have to write the electronic configurations, okay, and then for the neutral atom, and then you form the ions, okay, and remove the electron and form the new isoelectronic configuration for the ions. Then you compare. Okay, so variations in the ionic radii across period 2 and 3. Let's see the variations in the ionic radii. Okay, so we have the period 2 and elements in the period 3. So you can see that from the lithium to the boron, lithium plus to the boron 3 plus, the ionic radius become decreased. But suddenly, okay, the ion, okay, as I told you, okay, ions always larger than cation. But between these 3 anions, okay, it also decreased across period. Same for the period 3. Okay, for the isoelectronic species, radii decreases from the lithium to lithium plus to boron 3 plus, and 3 minus to F minus, and A plus to Al3 plus, and P3 minus to Cl minus. Why it happened? Because the proton number increases across period. So that's why the effective nuclear charge increases, and it will cause the attraction between the nucleus and electron become stronger. So that's why the the ionic size become decrease. So this is a variations of the ionic radii across period 2. So you can see that from the lithium to the lithium plus to the boron 3 plus decrease, and this one for the positive ion, and this one for the negative ion. But still the anions, okay, anions, the size of the anion decrease from the N3 minus to F minus. So this is the elements in the period 2. So across period 2, ionic radii of the cation decreases from the lithium plus to carbon plus 4 plus. So ionic radii, okay, decreases from the N3 minus to F minus. Actually, this one is the boron 3 plus. Okay, so but the ionic radii increases drastically, okay, from the B3 plus to N3 minus. Okay, why? Okay, ionic radii decreases from the lithium plus to boron 3 plus because the number of the electron is the same. It is the isoelectronic species. And what caused the ionic radii decreases? Because of the proton number increases, and it will cause the effective nuclear charge increases. So greater attractions between the nucleus and the outer electrons, and the size decreases. So that's why the arrangements of the ionic radii for the lithium is greater than beryllium 2+ and greater than boron 3+. There is a large increase in ionic radii between the B3+ to N3- ion because N3- has more shells, higher value of N. That's why it has a weaker attractions between the nucleus and outer electrons. That's why N3- increases. Okay, next, ionic radii decreases from the N3- to F- because the number of electrons are same. Okay, this also the isoelectronic species. But and from the N3- to the F-, proton number increases, so it will cause effective nuclear charge increases and greater attraction between the nucleus and outer electrons. So that's why the size decreases from the N3- to F-. Okay, this is the variations, okay, for the ionic radii across period 3. Alright, so you see that okay, from the sodium to the silicon 4+, okay, the ionic radii decreases, but for the anions, okay, it also decreases. Okay, let's see the variations in the across period 3. Across period 3, ionic radii of the cations decreases from the sodium plus to the silicon 4+. So ionic radii of the anion decreases from the P3- to Cl-. But the ionic radii increase drastically from the silicon 4+ to P3-. Why? Okay, this is because, okay, same as elements in the period 2, okay, because of the proton number increase, so it will cause the effective nuclear charge increases. Okay, so this is the same point. Okay, so this is a arrangements of the ions. All the ions are isoelectronic. So this is what happened, okay, when drastically increase, okay, because has more shells, okay, P3- has more shells. And this is the explanations, okay, for the anions. Same, okay, it caused by the effective nuclear charge increases, so greater attractions between the nucleus and outer electron. That's why the size decreases. So this is the arrangements, okay, for the ions in the period 3. Okay, that's all. Thank you.